Hello students, hope all are fine. Today we will discuss about the retaining wall. Retaining wall is an important structure in a structural engineering. Today we will discuss about various types of retaining wall, how to choose the dimension of retaining wall, what are the different factor of safety to be considered during the design of retaining wall. Engineered structures are often used to control the position of the soil, water, granular materials. These structures may take many forms such as dams, retaining wall, silos, tanks, culverts, tunnels, etc. To do their jobs successfully, they must resist the pressure applied to them by the material they support. In this video, we will discuss on how this force arise and the factors that determine their magnitudes. To understand how granular material generates pressure on a container, consider the box filled with wooden cylinders. Collectively, this cylinder produces downward force in the container. It is equal to their weight W. We could calculate this weight easily if we know the weight density of a material in the container. The material density is denoted by the letter gamma. In engineering, we often know the mass density rho of the material, and that quantity times g, the gravitational acceleration, gives the weight density. Next step is to determine the volume V of the material in the container. This can be easily found by multiplying the base area A by the container filled height h. To calculate the total weight, we simply multiply weight density to the volume. When we substitute these values in the equation we find earlier, we find that the weight is equal to the product of mass density, gravitational acceleration, base area, and container filled height. To calculate the vertical pressure PV on the bottom of container, we simply divide total weight by the base area. Substituting in our earlier equation for the weight and cancelling the area that appears in the numerator and denominator, it reduces to the simple equation. This equation tells that the vertical pressure PV is equal to the product of mass density of the material into gravitational acceleration and height of the material about the point which we considered. Please note, if we increase the height of a material, pressure increases. Wooden cylinder also exerts push force on the side of container. If we stop pushing them by the container wall, nothing stops them in pushing outside ways. To understand why this outward forces arises, consider three cylinders from the original stack. As gravity pushes the top cylinder downward, it tends to squeeze between the other two cylinders, pushing them outside ways. The magnitude of this outside ways force depends on how hard the upper cylinder pushes downward, and that in turn will depend on its weight and on the weight of a material that it supports. If the lower cylinder is constrained by structure, they will exert a horizontal force on that structure. At a shorter distance down, both the horizontal and the vertical pressure forces are small. At progressively greater depth, both pressure increases. Experiment shows that for most material, the ratio of horizontal pressure to the vertical pressure is constant. We call this ratio the pressure coefficient K, and it is usually less than 1. Thus, For granular material, the vertical pressure of any depth is typically rho g h, while the horizontal pressure is k rho g h. Clearly, then both the horizontal and the vertical pressure increases linearly with the depth as shown in graphs. The shapes and packing of particles in granular material affects the contact angles between them. These angles and coefficient of friction between the adjacent particles determines the magnitude of the outward pressure pH that is generated, and so they affect the value of K. If these ellipsoidal candies laid mostly horizontally, they will produce less horizontal force if they were randomly placed or if they were spherical. Also, if the surface of these candies becomes sticky, the lateral force will be reduced. As an extreme and practical example, sedimentary rocks sometimes contain horizontal layers like those formed by these wood blocks. What horizontal force will be produced? What is the associated K value? Since gravitational force are transmitted vertically from one wood block as of a piece of horizontal laid rock to the next one, no horizontal force or pressure results, and K, the ratio of horizontal to the vertical pressure, is equal to 0. Liquid represents the other end of the spectrum. Experiment shows that the liquid pressure are same in all directions, and so the K value, that is the ratio of horizontal to the vertical pressure, takes takes out as a value 1. In that case, we simply write the pressure P in any direction at a particular depth h is equals to rho g h. So in summary, the granular materials, the horizontal pressure pH is usually less than the vertical pressure PV as shown in the graphs and formulas for water and other liquids. However, the vertical and the horizontal pressures are equal. The single value P as shown in graphs and formulas.
In this slide, we will simulate the L-shaped retaining wall against wind force. Let wind flows from left to right. Here, in first simulation, leg of L-shaped retaining wall is pointed towards the wind flow. Let's see what happens. It is observed that wall overturns about vertical wall bottom leeward corner, also denoted by pivoting point P. Here, two types of moments are acting. First is the overturning moment MO, acting in clockwise direction, developed due to the wind force FW, acting towards positive x direction at a distance y from pivoting point P located at the bottom right corner of slab base as shown in the slide. The second is the stabilizing moment ms acting in anticlockwise moment direction developed due to self-weight W acting at a distance x from pivoting point P. Since MO, that is an overturning moment, is greater than a stabilizing moment MS, our L-shaped retaining wall, which is having its leg projected towards the wind, shows overturning failure. Now consider the case 2 of the slide, where projected leg is pointed away from the wind. Let's see what happens. It is observed that wall is stable against overturning but fails in sliding. We will discuss the sliding failure in our upcoming slides. Presently, we will concentrate on overturning failure. Here also, two types of moments are acting. First is the overturning moment MO acting in clockwise direction developed due to wind force Fw acting towards the positive x direction at a distance y from pivoting point P located at bottom right corner of the base slab as shown in the slide. The second is the stabilizing moment Ms acting in anti-clockwise direction due to self-weight W acting at a distance x from pivoting point P. Here you can see that our lever arm X is much larger compared to the lever arm in our case number 1. Since our overturning moment MO is smaller than our stabilizing moment MS, our L-shaped retaining wall, which is having its leg projected away from wind, is stable as far as overturning failure is concerned. Now, in this slide, instead of wind force, let the force is applied by granular material. With respect to the previous slide, can anyone guess which case is more stable? Whether it is a case number 1 or a case number 2. In our previous slide, case number 1 shows the overturning failure while case number 2 is stable as far as overturning failure is concerned. Would retaining wall in this slide will behave in the same manner? We will pause our video for some time for your guesswork. What is your guess? I think most of you think it's case number 1. Let's see what actually happened in the simulation. Haha. Here case number 2 is unstable and not case number 1. This slide totally contradicts our previous slide theory, saying that if the projected leg of retaining wall is in a leeward direction is more stable than that of its mirror image. Why it is so? Let's understand the reason. In case number 1 of this slide, a part of force that are observed in our previous slide, one more granular gravity force is also acting, which is getting added to the stabilized moment ms. Hence, if we have enough length of projected leg, our ms will be greater than our mo, making the system stable against overturning. In this slide, we will see the behavior of retaining wall with different base slab length. In first case, the base slab length is enough to generate a stabilizing moment to be greater than an overturning moment. In second case, with decreased base slab length, though the stabilizing moment is greater than an overturning moment, retaining wall slides towards the right as frictional force between the retaining base and a container surface is less than the horizontal force exerted by granular material. In last case, with least length of base slab, overturning moment dominates the stabilizing moment, resulting into retaining wall to have an overturning failure. Last three slides are designed to develop a general understanding of the direction of projected leg and importance of the base slab length against a sliding failure. It is observed that projected base slab should be beneath the granular materials with enough leg length to avoid sliding failure. Okay, now question may arise, can retaining wall can be used in a dam-like structure? What happens if the granular material is replaced by liquid? Let's see that in this slide. You might be surprised that L-shaped retaining walls are seldom used as dam. The reason is the pressurized water in the dam may seep under the base of retaining wall, and if it does, the resultant upward water pressure on the bottom of a retaining wall can generate an additional overturning moment and make the dam overturn. Projected leg of L-shaped retaining wall will generate a large lever arm resulting into the large overturning moments due to the vertical seepage pressure in addition to the horizontal pressure generated due to the vertical column of water. Let's see this in our simulation. I would like to repeat my statement again. Projected leg of L-shaped retaining wall will generate a large lever arm resulting into larger overturning moments due to a vertical seepage pressure in addition to the horizontal pressure generated due to the vertical column of water. You can see this in our still photography also. In addition to this, water at the bottom of base layer will also act as a lubrication, will result into a lower frictional resistance against sliding. While in case number 2, by eliminating the projection of leg, seepage pressure to a larger extent gets eliminated. Thus, the dam is stable if the weight of gravity retaining wall is enough to resist a low seepage pressure generated due to smaller base width and a vertical water column pressure. We will see this in our simulation. With this slide, I want to develop the understanding that in liquid retaining structures, the weight of water on projected leg does not help much in stability of dam. Rather, if seepage occur, and which occurs most of the times in dams, may be the prime reason for dam instability. Here, I would like to develop a way-back slide developing the understanding of water pressure coefficient K is unity. That is, water exerts same pressure in all directions whether it is vertical or horizontal. While for a granular material, K is always less than a unity, which means that vertical pressure will always be greater than that of an horizontal pressure. Hence, granular material which are able to generate a large vertical pressure on projected leg of a retaining wall than that of an horizontal pressure on a vertical stem of a retaining wall. L-shaped retaining wall are more justified for the use of retaining the granular material than that of a liquid material.
In today's lecture, we had gone through various type of retaining structures, understanding of vertical pressure of material, theory of understanding the reason of generation of horizontal pressure, granular and liquid pressure coefficient, importance of contact angle, shape of material, its stickability property, etc. We have gone for an in-depth understanding of L-shaped retaining wall, its orientation, and the effects of retaining material on a retaining wall. In our next lecture, we'll go for in various types of retaining wall, various components of a retaining wall, understanding of active and passive soil pressure, derivation of active and passive soil coefficient, forces acting on retaining wall, various stability conditions applicable to retaining wall, etc. With this, we conclude our lecture. Thank you.